In this video, we will look at the following problem. An astronaut is massing mice to study bone loss in the weightless environment of space. To do so, she puts an empty cage on the end of a spring and starts it oscillating with a period of 0.12 seconds. She then adds a mouse to the cage and sets it oscillating again with a new period of 0.14 seconds. What is the mass of the mouse? As always, we start off the problem by drawing a picture. In this case, we have two situations. We have the empty cage that has a period of 0.12 seconds. Then we've got that same cage, but the cage has a mouse inside of it. And we have a new period of 0.14 seconds. Next, we want to think of the idea for this problem. In this case, we want to use the idea of simple harmonic motion. Specifically, we need something that relates the period to the mass. That formula, if we look it up, is as such. Omega is equal to the square root of k over m, where k is the spring constant and m is the mass on the end of the spring. We can relate omega to the period because omega is the angular frequency, defined as 2 pi times the typical frequency, and we know that frequency and period are inversely related.
Using this, we can now go about trying to solve the problem. Substituting these expressions into our equation, omega equals square root of k over m, we get 2 pi over t is equal to the square root of k over m. If we look at the second situation, where we have the m is going to be the mass of the mouse plus the mass of the cage. So we have 2 pi over t is equal to the square root k over the mass of the mouse plus mass of the cage. Solving for mass of the mouse, we get 4 pi squared over t squared is equal to k for mass of the mouse plus mass of the cage. I'm going to move everything on this side over here by dividing both sides by t squared and multiplying dividing both sides by 4 pi squared and multiplying both sides by t squared gives us 1 is equal to k over mass of the mouse plus mass of the cage times t squared over 4 pi squared. Then I'm going to multiply both sides by the mass of the mouse plus the mass of the cage. Mass of the mouse plus the mass of the cage is equal to k times t squared divided by 4 pi squared. Finally, we're going to get that the mass of the mouse is equal to that expression we have minus the mass of the cage. We're almost done, except now we need the spring constant k. To find the spring constant, we have to go back and look at our initial problem. We have this situation to look at, and that is the oscillation of the empty cage. We can use the same expression, but this time we're going to solve for k. This gives us, again, 4 pi squared over t squared is going to be equal to k over the mass of the cage. Solving for k, we simply have to multiply both sides by the mass of the cage. K is equal to 4 pi squared over t squared times the mass of the cage. At this point, we need to combine these two underlined equations to solve for the mass of the mouse. Now, I do want to point out that I should have labeled this as T1 and T2. This is T1, this is T2. Those are not the same values for T. But going on and substituting in for K into this equation, we're going to get that the mass of the mouse is going to be equal to T2 squared over 4 pi squared times this K, which is 4 pi squared over T1 squared, times the mass of the cage minus the mass of the cage. The 4 pi squareds cancel, and we get an expression that the mass of the mouse is going to be equal to T2 squared divided by T1 squared times the mass of the cage minus the mass of the cage itself. Plugging in values for T2 and T1, we get 0.14 seconds squared divided by 0.12 seconds squared times 100 grams minus 100 grams. Plugging those values into a calculator, we get that the mass of the mouse is 36 grams.